It's the first time I will be. Yes, welcome everybody. Good morning, evening, night. So we are here now with Professor S.R.Das. So he's going to talk about the comments on target space entanglement. So please welcome Professor Samit.
Okay. Let's begin by thanking the organizers for inviting me to give this talk in this conference. It was a good idea to organize this conference. So I'll talk about something which I've been thinking about for quite some time, but got around to writing something just last year and some work. And these are the two papers which I'll be talking about together with some results which have not yet appeared. A familiar kind of entanglement in quantum field theories is what I'll call an entanglement in base space. This is the notion of entanglement of the degrees of freedom which are localized in sub-region of space. And we, starting, for example, with a wave function, we start with the pure state for the entire system. There's this familiar description of the density matrix, which
Excuse me. We are not seeing any transparency. Is there any PowerPoint there? No, I think you don't.
Maybe this shared screen didn't work. Just 1 second. Let me try again. Does it work now?
Yeah,
it works. Yeah.
But okay, so let me go back one more step.
Yeah, maybe you need to enlarge it.
Is it okay?
Yeah, that's perfect.
Good.
Thanks.
Okay, so this is what I was saying, that this is the most commonly studied form of entanglement. An alternative way of thinking about such entanglement is in terms of a subalgebra of operators. I mean, in this case of a usual quantum field theory, the subalgebra are the operators which are localized in that region A. If I have an explicit form of the field theory, these are all operators which are made out of the fields and their canonically conjugate momenta, provided they are located in A. And the reason for this is that these are the operators which can be used to perform measurements in the region A. This talk will deal with the notion of entanglement in target space of a field theory. So as I will go on and explain what I mean, because there are more than one notion. One of the motivations for thinking deeply about target space entanglement comes from holography. We now know that there is a lot of evidence for a deep connection between the emergence of smooth geometry and base space entanglement of the boundary theory. However, in examples of holography which come from string theory in particular, the base space of the bulk theory emerges out of part or whole of the base space of the bulk theory emerges out of a target space of the holographic dual. For example, in usual string or M theory examples, the bulk lives in space-times which are like ADS M cross YN, and the internal space arises out of the target space of the field theory which lives on the boundary. It is therefore natural to suspect that there is a similar connection between emergence of smooth internal space and entanglement in the target space. For examples where all the space directions are emergent, and we will talk about some such examples in much more detail, the target space entanglement should be relevant for the smoothness of the entire bulk. Since the bulk space comes from the target space of the boundary field theory, it is therefore also natural to expect that target space entanglement should be related to bulk entanglement. Of course, the bulk is a theory of gravity. So in a theory of gravity, there is no exact notion of a region of space, and therefore there cannot be an exact concept of a bulk entanglement entropy. However, what we will speculate is that in classes of holography theory with bulk duals, the notion of target space entanglement which is very well defined, provides an approximate notion of entanglement between regions in the bulk, provided there is a regime where this what I call regions in the bulk makes an approximate sense. Much of our considerations actually came from a calculation which I did back in 1995. And this calculation has got to do with the two-dimensional non-critical string. This is, in fact, one of the earliest examples of emergent space preceding the ADS-CFT correspondence, and a very well understood duality between two-dimensional non-critical strings and gauge quantum mechanics. So what we have here is a single n by n Hermitian matrix M, which is gauged. AT is the gauge field, and the action involves a covariant derivative, which involves the AT. Now, this, of course, in one dimension, there is no space in this theory. It's just time. It's regular quantum mechanics. So in one dimension, I mean, the one time dimension only, the gauge field is rather trivial. However, it does live to a Gauss law constraints where all the states are singlet. So therefore, using the gauge invariance, we can go to a gauge where AT equal to 0 when we are left with global transformations, and we can use these global UN transformations to make the matrix diagonal. This, of course, completely standard and dates back to the 1980s, this treatment. And as is well known, because of a non-trivial Jacobian, which comes from transforming the variables from the matrix to the eigenvalues, these lambdas become coordinate of fermions. They become coordinates of fermions because there is a remaining symmetry after you have done all the gauge fixing, which is Weil transformations, which is the interchange of these eigenvalues. In the double scaling limit, the theory simplifies considerably, and what we are left with a part of the potential, which is only the inverted harmonic oscillator. I'll not go into the details of that. Now, this being a theory of n fermions, you can always rewrite this in second quantization. This is simply a change of language. It's an exact rewriting of the theory. And this is the Hamiltonian of a second quantized fermion theory in such a background. I've introduced a kind of a Lagrange multiplier term. Let me get the pointer. A Lagrange multiplier term to impose the condition that the total number of fermions is equal to n. So in this language, the space of eigenvalues becomes an emergent space direction. However, this is a non-relativistic theory, so this is not really space in the way we think about in relativity. But nevertheless, there is a usual notion of entanglement entropy of a region of the X space with the rest. We have a quantum field theory, a non-relativistic quantum field theory, and we can definitely use the standard definition of entanglement between one region of this eigenvalue space with the other. So as I mentioned, I did this calculation without understanding too much about what I am calculating. And this calculation has been more recently revisited by Hartnell and Mazeng, who used improved techniques of calculation of such entanglement due to, there's a large literature on that, in condensed matter literature on that problem. And here is a final result when the interval is far away from the hump of the potential. Here Q1, this coordinate Q is basically the eigenvalue coordinate after a local transformation. And what appears in this entanglement is you find is a familiar form of an entanglement of a two-dimensional theory. However, in usual quantum field theory, as is well known, the entanglement entropy is necessarily, in usual relativistic quantum field theory, as we know, the entanglement entropy is necessarily ultraviolet divergent. This answer is, however, completely finite which has got to do with the non-relativistic nature of the problem. But what is significant is the thing that makes it finite. The thing that makes it finite is what I'll call an effective coupling, which I'll explain why this is the effective coupling in the next slide. The way to understand that why that is the effective coupling is to go over to a description in terms of a collective field, which is the density of eigenvalues. One can rewrite the theory exactly in terms of this collective field. And as is usual in large N, there is a saddle point of the collective field. You expand around the saddle point, and this one is the action of the classical action of fluctuations around that saddle point. What you will notice here, I have gone over to the Q variables. And in terms of the Q variables, you immediately find that this part of the action is completely relativistic in 1 + 1 dimensions. In fact, this is a relativistic massless scalar in 1 + 1 dimensions. And the usual massless tachyon of the 1 + 1 dimensional string theory is related to this field by a transform, which is non-local in space, but the non-locality is given up to the string length. There are interaction terms of these fluctuations which become identified with the string interaction terms with a coupling which is space dependent. And this is the quantity which appeared in the previous slides as what provides a cutoff for the entanglement entropy. So the notion of the entanglement of the fermionic degrees of freedom provides a notion of the entanglement of the string field. In this case, the string field basically collapses to a quantum field because, as is well known, the only dynamical degree of freedom of 1 + 1 dimensional string theory is a massless scalar. All the others are, they're not dynamic. There are no waves of the other higher modes. They can be backgrounds. So the notion of entanglement of the fermionic degrees of freedom provides a notion of entanglement of the string field up to a fuzziness of the order of the string length. We could have treated the scalar field theory perturbatively, as you would have done if you were dealing with the low energy effective action of this 1 + 1 dimensional string theory. And you would, of course, get a logarithmically divergent result. And as I emphasized, the exact result from the fermionic theory is finite. And the UV scale that makes it finite is not just the string length, but in fact the string coupling. Therefore, this would be quite invisible in perturbation theory. Now, this is a well-defined calculation with a well-defined result. What we would start to understand is what is the meaning of this quantity in matrix quantum mechanics. The meaning of this quantity in the 1 + 1 dimensional fermion non-relativistic fermionic field theory is quite clear, but we would like to understand this in terms of the matrix degrees of freedom.
Shumit, before going on, if you did the same thing for BFSS type matrix model, how would this change?
Of course, such a calculation, part of my talk is to how to set up such a calculation. So maybe...
Okay, I'll wait until...
We have a guess for what the answer would be, but I have no idea whether our guess is right.
Okay, so...
Okay. I mean, a lot of the rest of the talk will actually deal with the BFSS. Okay. So to begin understanding what is it in terms of the matrix degree of freedom, let's first try to understand what is this quantity in terms of the first quantized description of fermions. So what we have are n fermions, which are living in some external potential. It's a very standard kind of problem which comes up in many areas of physics. Now, these are identical fermions. So the physical observables are all sums over the individual fermionic operators. So I've written so these are many body operators which I've written down in this form, where lambdas are the operators which correspond to the coordinates of the particles, and pi's are the canonically conjugate momentum. And typically one would like, for example, to calculate expectation values of this quantity. For example, just ignoring complications due to the conjugate momentum, let's think of calculating this quantity, which is the nth, which measures the nth power of the position of each particle and sums over all particles. Of course, being a theory of identical particle, referring to a measurement on one particle doesn't make any sense. I mean, and as the way it comes from the matrix model is that this symmetry, which makes this identical particles, is actually a gauge symmetry of the underlying quantum mechanics. Now, suppose we have the ability to make measurements only if the particle is in some region A of the real line. So this restricts us to operators which forms a subalgebra. It turns out that the subalgebra can be obtained by defining a projection operator, which I've written down here. And then we construct a new operator by replacing each of the individual operators by their projected versions. So they have written down in gory detail what would be the projected operator for this CNM, which I introduced in the previous slide. For example, if there were no momenta, this projection operator only contains the position, so they'll all commute and you can all bring them together, and then it becomes very simple. This operator, of course, in the second quantized language is the standard object, the nth moment of the density, of the fermion density. Now consider the expectation value of such an operator in a pure state. It's an easy exercise to stick this operator, this projected operator, in between the two states, and this is the result for two particles. For example, I've taken an operator which is 3 powers of the lambdas, and I have stuck in the wave functions, and I get 2 terms. The first term has an integral over the coordinates lambda1 and lambda2, which are entirely in the region A. The second term, one of the integrals is over region A, the other integral is in region A bar. And it is quite clear, if you look at the second term, the thing that appears here is only lambda1 cube, namely the coordinate which belongs to the region A. A bar is, of course, the complement of it. So what this operator is doing, it is measuring the cube of the position of the particle only when it is in the region of interest A. So this makes it the mathematical expression of the fact that you are only allowed to make measurements if the particle lives in a region A. And this, of course, generalizes in a trivial fashion. What this means is that the Hilbert space is not a direct product Hilbert space, but we can become a sum over sectors. And each sector is a direct product. And the sectors can be labeled by the number of particles K, which lie in the region of interest, in a way which is sometimes similar to usual entanglement in gauge theories. Acting on a state in this sector, the operator has a non-trivial action only on those particles which are in A. Therefore, we can think in terms of an operator OK, which lives in the smaller Hilbert space, which pertains only to the region of interest. This means that the entire answer can be rewritten in terms of a reduced density matrix. And the reduced density matrix also lives in this smaller Hilbert space, which is this direct sum. And this is an explicit expression for the reduced density matrix. It is important to note that the way we have defined the reduced density matrix, it is not normalized. In fact, its trace is simply the probability that K of the particles lie in the region A. The full reduced density matrix, which takes into account all the sectors, is of course normalized, as there's a way of writing the full density matrix, and each thing is a sector, which is labeled by K, which runs from 1 to n. And so therefore, we can use this full density matrix to define an associated entanglement entropy. And you can rewrite this by using this decomposition as a sum of trace over this kth subsector. This generalizes, I've illustrated the construction when the state of the entire system is in fact a pure state, but this construction, the projection operators and things like that, they all generalize in a very trivial fashion when the entire system is in a mixed state, for example, the thermal state. In the ground state, the wave function is an anti-symmetrized product of single particle wave functions. And each of these are spread over the one-dimensional line. In this fairly delocalized wave functions, we are making measurements using detectors which are placed only in region A. It turns out that this entropy, you can use this expression to rewrite the entropy in this following form, which has two terms. The first term you can recognize is what we call a classical piece. This is just the piece of a classical set of particles, pk, because pk is the probability that the k particles are living in this region. The second part is non-trivial, and this is a second part which is usually associated, which are called what are called distillable parts of the entropy. In fact, just to emphasize the nature of this concept, we'd like to emphasize this notion exists even if there is just a single particle. There's nothing wrong in considering a single particle. And in this case, you can see that the answer for the entanglement entropy is just completely classical, where PA is the probability that the particle B is in the region. And this brings forth the point that this is not an entanglement between particles, because there are no two particles, there's just one particle. The entanglement and the mixed reduced density matrix comes about because of your inability to make all possible measurements which would be able to detect the particle everywhere. You can only detect the particle if it is in some particular region of space. In fact, there's nothing wrong in writing the quantum mechanics of a single particle in a second quantized formalism. I mean, it's not very useful, but you can still go ahead and do it. And this will agree with the usual notion of base space entanglement. And that, of course, generalizes to n particle. And you can prove, in fact, that, and this is in one of the appendices of one of our papers, that if you have n particles, n fermions, then the base space entanglement in the second quantized formulation is exactly this entanglement in the first quantized formulation.
Just show me before going on. This entanglement is there because you start with the non-relativistic quantum mechanics, right?
Correct. Right. Because there's a notion of the number of particles.
Okay. Because and we know that non-relativistic quantum mechanics has some non-locality inherent in it, and this is a manifestation of this.
I wouldn't say it's because of the non-locality. I think I would say this is arising because in the non-relativistic theory, where you have a fixed number of the notion, I think this probably holds even for relativistic theories where there is some kind of a charge, or which is, and you can ask for a set of measurements which tells you that I can only measure operators of a given charge. Of course, the non-locality is, I mean, the ground state wave function of relativistic theories are also non-local. So I think, you know,
right.
that part is of course always there, I think.
Yeah, actually, yeah. I was trying to see whether I can think of this entanglement as some non-locality in quantum mechanics. So that was sort of.
I'm not sure. Maybe you can, but I'm not sure, I think, of that.
Okay, thanks.
Okay, I'll think about it. Okay. I should emphasize that even though we use free particles, which move in some external potential, The same concept and the same construction, of course, works for interacting particles. I mean, of course, when you have an interacting system of interacting fermions or bosons for that matter, the fact that there are interactions will manifest itself in the nature of the ground state wave function. So nothing in the concepts is actually tied to the notion of free particles. In fact, this makes it interesting. This one of the directions which are pursuing at the moment is that this quantity is therefore of great interest in many body systems. Very often, the wave functions of these systems, for example, the quantum Hall effect, are known in the first quantized formulation. It's sometimes not that easy to write it in second quantized formulation. And then our construction can then be used to understand entanglement in these systems. I should also mention that in such systems, one often defines something called a K-body density matrix. This is common in the quantum chemistry literature. This density matrix evaluates all K-body operators, regardless of the location of the particles. By construction, the reduced density matrix with what we call the target space entanglement is quite different from this. Furthermore, some notion of target space entanglement, though it's not very clear in our mind what this notion is implicit in worldsheet calculations of entanglement entropy in string theory, which have been explored by various authors. But as I said, we don't completely understand what this calculates. This calculation is usually done in a what is called a conical entropy, or already in the replica in terms of the replica method, and it's not clear in our minds what that calculation really is. It will be interesting to understand any connection. Okay, so far we understood that n fermions on a line is secretly gauge quantum mechanics of a single matrix. In the gauge, when the matrix is diagonal, and we already understood that what are the operators which belong to the sub-algebra in this gauge. Our main motivation is to generalize this to multiple matrices. So to begin with, we want a gauge invariant specification of this quantity. The set of gauge invariant operators in terms of the matrix degrees of freedom and its canonical conjugate, for example, can be written in this particular form. It turns out a construction which is entirely similar to what we did for the particle quantum mechanics also provides a notion of target space entanglement directly in terms of these matrices. So you define a projection operator, which is a matrix valued operator in the Hilbert space, which is defined as an integral like this. I should say M is a matrix operator, and I is the identity operator, and X is a number. Then the gauge invariant operators belonging to a subalgebra are obtained by replacing each matrix in this string by its projected version. And it is easy to check that in the gauge, when the matrix is diagonal, this reduces to the operators which we just discussed. I mean, that can be easily verified by taking this explicit formula and using the gauge where the matrix M is diagonal. So this projection operator therefore specifies in a gauge invariant way the degrees of freedom which are being traced over. So this brings us the generalization to multiple matrices. For example, BFS's D0 brane theory. This is the well-known action. And of course, we cannot choose a gauge where all the matrices are diagonal. However, the construction for the projection operator remains in fact the same. I'll give more examples of that because that's a gauge invariant thing. For example, consider the set of matrices Xi and consider a function of these matrices f of Xi, which is a matrix valued operator in the Hilbert space. And we define a projection operator, which I wrote by in exact analogy with this. And here is an example. For example, when f of xi is, just take the first matrix x1 minus a number, then it is easy to see that this projector leads to a subalgebra of operators which results from the condition that the eigenvalues of this Hermitian matrix operator are positive. So in this case, in the case when f of xi is just x1 minus a, then you can see that what it does is to project the operators onto the sector where some number of eigenvalues of x1 is greater than a. The above projector therefore imposes a target space constraint that the eigenvalues of x1 are greater than a. And pretty much like the example of n fermions, what this would do, so the way we would do it, I mean, for example, if there is a complicated combination of these matrices, like the capital R hat square minus R naught square, where this is like the radial coordinate in the matrix space, the constraint would be that the eigenvalues of R square are greater than R naught square. Okay. And pretty much like what we had for the fermions, the Hilbert space will break up into subsectors, and each subsector will be characterized by how many of these eigenvalues lie in my interval which I have chosen. Okay. So here is an explicit construction of these operators. You start with the general operator, which is a string of x's and the pi's, and we get the projected operator by doing these projections. And for example, if you had for example, just to illustrate what this does for this simple constraint, the way to see what this is doing is to go to a gauge where x1 is diagonal, the others are not diagonal. So the x1 has some diagonal matrices which are lambda 1 to lambda n. The pi's are also diagonal matrices pi 1 to pi n. They are, of course, all of these are operators in the Hilbert space. And once I go to this gauge, the remaining gauge symmetries are, of course, the Weil transformations and U1 n transformations. What the Weil transformations do is to do permutations of these eigenvalues and mix up the other matrices which are not diagonal in non-trivial ways, which I've indicated out here. The U1 to the n transformation acts on the matrices which are not diagonal by sticking in phases which correspond to what of diagonal matrices we are talking about. So these are remaining gauge symmetries which the theory must respect. So we have to impose this gauge symmetry explicitly on wave functions. This is the analog of going to the subspace which satisfies the Gauss law constraints. For example, one may use a basis in the Hilbert space where the eigenvectors of the operators lambda and x, these lambdas and x, when I say eigenvectors, I mean eigenvectors in the Hilbert space. So clearly as operators in the Hilbert space, they can be simultaneously diagonalized. And so in terms of this, a basis for such basis for the states which respect the gauge conditions is given by symmetrizing with respect to the Weil transformations and integrating over the U1 to the power n transformations. Now we already know that in this gauge, the projector picks out the eigenvalues of x1 which are greater than a. And as I said, once again, there are sectors which are labeled by the number of eigenvalues k which satisfy this condition. The non-trivial thing is to ask, what does this projection do for other matrices which are not diagonal? It's actually easy to see that the projector which we define retains all the operators in this k by k block. I would emphasize that this is the description in this particular gauge. Of course, our definition is completely gauge invariant. Now, it turns out that it is also possible to construct a projector. It's a different projection and therefore give a different notion of target space entanglement, where not just a k by k block, but this rectangular n minus k times k and k times n minus k are also retained, but let me not go into that. To illustrate some other non-trivial constraints, you can obtain an interesting set of subalgebras which can be obtained by performing a polar decomposition of the matrices. And one way to do this is to combine, for example, in the case of two matrices, x1 and x2, you could introduce a complex matrix, and this expression here is like a polar decomposition of the complex matrix. And so we worked out how this thing actually works for an arbitrary number of these matrices. So let me not again go into the details of that. And once again, you can, for example, require that the eigenvalues of this radial matrix, which is this complicated object which I've defined here, are greater than or less than a certain, or you could restrict the eigenvalues of the unitary matrix Q. So this is a decomposition of a complex matrix in terms of a Hermitian matrix and a unitary matrix. So you can also impose the condition the eigenvalues of the unitary matrix lie on some range. And that's also a trivial thing to do. Okay, I'll not go into the details of the formula, which quickly become rather complicated, but mention that since this is an explicit construction, we can obtain, in fact, Euclidean path integral expressions for the Renyi entropies in terms of paths in the space of matrix elements. And these are expressions which will be needed if you want to do explicit numerical calculations of this entanglement entropy, which we are pursuing at the moment. So for example, for the second Renyi entropy, it's a sum over complicated paths. If you're interested, I can explain this, but let's ignore that. What about DP brane theories?
Shumit, before going on,
yeah,
I'm just trying to see if I am following. So far, your discussion and the equations did not really rely on the fact that the potential in the BFSS is just like a commutator square. It's true for any potential, right?
Absolutely right. Of course, that will come in when you actually think of what state you are working in, like the ground state.
So there are two questions here. Here the potential has flat directions, and I was wondering how does that change? Of course, this part is pure kinematical, and you're right.
Yes,
that
this is completely kinematics, right?
Right. But when we have flat directions, then I would expect that the result of the actual computation should have some divergences somewhere. Right, because of the flat direction.
That's, of course, with a finite number of degrees of freedom, I don't know why the divergences would come.
No, this is a large n result.
A large n. At large n, yes, there will be a divergence. And as you can see, like in our previous examples, those answers were also divergent when n was infinity. In fact, that's one of our points, is that these things are divergent when n is strictly infinite. It's a finite n which makes these things finite.
Okay, so but still I would expect that the flat direction, the potential should show up somewhere.
Absolutely. I mean, for example, when you are doing an explicit calculation with a wave function, as you know very well, that in the flat directions are very important there. Absolutely.
And the other question is, in the BFSS metrics theory, we also have fermions. It's a supersymmetric quantum mechanics.
Right.
And would you say the same thing for, I mean, how would the fermionic degrees of freedom come into this?
Yeah, they would be in a very similar fashion, actually. I mean, you could, the fermions of their fermionic, but they're still, like quantum mechanical operators. So you could again, use this kind of projector where, where you have a functional of this fermionic operators. We haven't worked out the details of that, but we feel that I'm not saying they would be completely identical, but it would be quite similar, I think.
'Cause, I was just curious to know what would you replace for the projector. That's, I think, the non-trivial part.
Right. So for the projector, it's the place where the matrix X appears, there would be a psi. So it will be a fermionic object, but again, if you take, let's say, one of the psi i's, psi alphas, let's say, the fermions, I mean, that also is, I mean, generally a complex matrix, but you can write it in terms of, two real matrices, each complex psi, and you can similarly, have a gauge. Maybe you're asking whether
they are Grassmann values.
If you diagonalize one of the x's, they will probably not diagonalize the size. So it has to be a different gauge choice.
Yes, exactly. So and then there are Grassmann values. So the delta functions would, which appear in the projector, would not be really similar to the X case. So.
Well, we were thinking in terms of an operator formulation where psi is not really a Grassmann number, but just a fermionic operator. I mean, their eigenvalues are Grassmann. I mean, the eigenvalues of the psi will be Grassmann objects.
Yes, and that's what I was wondering.
Right. So that small x which I wrote there also probably needs to be a Grassmann object. And
exactly.
Yeah, it might be interesting to figure that out. We never actually sat down and do it, but I think conceptually, I think it will be quite similar.
Yeah. So then, thank you.
Yeah. Okay. So for DP brains, things can become very interesting, but it is trivial when you impose the same target space constraint for all points on the DP brain base space. And I'll not go into more details of that. I mean, it's actually completely similar. But however, now we have a richer possibility, which we haven't explored completely, but in the process of doing so, where you can impose target space constraints which apply to part of the base space. So this will be a mixture of base space and target space constraints. And in particular, I mean, there would be connections to another notion which many people have explored, is the notion of entwinement. And these are again things we haven't gone to the bottom of these things as yet. Okay. Now, for the case of a single matrix, the target space entanglement entropy had a bulk meaning. This is simply the base space entanglement in the fermion field theory. And up to effects of the string length, this gives the notion of bulk entanglement in the field theory of the massless tachyon. We want to explore if there is a similar meaning for DP brane models. For example, for D0 branes, the classical ground state has commuting matrices, which can be chosen to be diagonal by a gauge choice. The eigenvalues are then identified with the location of D0 branes in these D directions, where D is the number of matrices. So therefore, at the classical level, the off-diagonal matrix elements are open strings with joining the branes. This is the standard picture. In which case, the entanglement associated with the target space constraint is then naturally identified with the region of the bulk associated with the constraint, the same constraint where the xi's are replaced by the bulk coordinates. I'll come to some problems with this later on, but let's see what does that mean. For example, a typical snapshot of a configuration of the eigenvalues, suppose I take two matrices, two 3x3 matrices, and I look at it in the gauge where one of the matrices is diagonal with diagonal entries lambda 1, lambda 2, lambda 3. The second matrix is this given by this. So a typical configuration can be pictorially represented in terms of these eigenvalues and open strings which join these eigenvalues. a constraint which sets x1 greater than 0 with the using the projector P1, then is going to keep this 2 by 2 block of x1 and the 2 by 2 block of x2. In terms of the picture, what would mean is you retain the reduced Hilbert space is now composed of the open strings, which are these degrees of freedom, which lie entirely in this region. The second projector, which I didn't talk about much, can also keep the open strings which join the the D0 brane, which lies beyond this region. In a similar spirit, if you take a constraint which involves the radial coordinate r, you might think would be associated with the bulk region, which is a spherical bulk region. And as I said, we'll come to some caveats later. In the quantum theory, this naive picture, as is well known, does not generally hold at strong coupling. However, we can use this picture for states where the dominant configurations are branes which are far separated. These states may or may not be among the low energy states, which are also described by the supergravity rule. And as is well known, this is actually tricky for D0 branes. Nevertheless, for reasons which are not completely well understood, this naive picture of the eigenvalues representing location of D0 branes and the off diagonals of the other ones representing open strings does seem to hold for whatever is known about the ground state wave functions. In this theory, the ground state wave function is not analytically known. There are various approximations which people have explored. And it seems that in certain regimes, some of this is in fact whole. Things may be a little bit better for higher dimensional branes where there is a genuine Coulomb branch, which corresponds to multi-center solutions in the bulk. Maybe the situation is better. Recently, an interesting paper by Hampapura and Lawrence have used this kind of construction and a Born-Oppenheimer approximation, which may or may not be completely well justified, but possibly gives a good picture, to calculate this kind of quantities. So what they have considered are a well-separated D0 brane and concentrate on a fixed sector with a given number of branes in the region of interest. In this approximation, the slow modes are the eigenvalues and the fast modes are the off-diagonal elements. In this setup, it is therefore natural to consider the first version of this projector, and they have a setup where they characterize this sector by the U1 charges with the visible links. At the end of the day, what they find, there is in fact a result which is proportional to the square of the number of branes in the region of interest. So far, we have dealt with a sort of a bulk space as perceived by D branes. It becomes problematic when we start thinking of target space entanglement, which relate to measurements of bulk modes like gravitons and dilatons. At least in the semi-classical regime, where the theory of gravitons and dilatons can be thought of as a usual quantum field theory in some curved space, there is a notion of entanglement, which is of course approximate. And the question is, does it actually agree with this notion of entanglement, which we have discussed, which is very much tied to the space as perceived by D0 branes? We don't have a definite answer, but I think probably not. I think they may be different notions, but they might capture some aspects. And these are the observations which can be obtained by the motion of probe branes in the region of interest. I mean, the rough idea is that if you have a probe brane which is moving in some space-time, the probe brane can detect by its motion gravitons and dilatons, and to a good approximation, these would be the gravitons and dilatons which are very close to these probe brains. So there should be some aspects of it, of this entanglement of these modes, which can be captured by the entanglement of D0 brains. However, there are reasons to believe that this description of supergravity modes in the region of interest has to be approximate. One could, for example, define bulk field operators by the standard BDHM-HKLL procedure, which involves low energy simple operators of the gauge theory. And it turns out that the probe brains will not suffice for measurements of all correlators of these bulk fields. For example, the Hamiltonian of the system is not in the subalgebra we are considering. Whereas in the HKLL procedure, and if we take a region which is a spherical region, the Hamiltonian would be in the subalgebra. And if it was, there is an argument which shows that the entanglement entropy of such an annular region near the boundary should in fact be zero. Our answer is clearly non-zero. Nevertheless, the definition of the target space subregion is precise so far as the D-brane theory is concerned, and this leads to an exact subalgebra. Its identification of the bulk region is only approximate. I should also mention there are other notions of target space entanglement which may be a little more natural from the point of view of bulk reconstruction of supergravity modes. For example, consider the case of D0 branes, where one can consider a linear combination of usual spherical harmonic operators such that they correspond to supergravity modes which have support of a subregion of the 8-dimensional sphere. One might try to assign an entanglement entropy with the algebra of operators generated by the subset. I mean, though we don't really have explicit formula for doing that. And it has been speculated in the past that this may be evaluated to leading order by an extremal surface which is anchored on the boundary of the subregion. The notion is different from what we have been discussing, but we need to understand this connection a little bit more. Now, I'm running out of time, so let me skip some part of it. One thing I would like to emphasize again, since our construction is very explicit, they can be used for numerical calculations, which have been very successful for D0 branes, since we have path integral expressions, and we are pursuing this. But let me end with a kind of a conjecture, which may be right or may be wrong, by asking what could the answer be if you were able to do such a calculation. As I emphasize in two-dimensional non-critical string theory, where there is a calculation, the UV scale, which makes the entanglement entropy finite, involves the coupling and not just the string length. Now, in the context of holography, the coupling is 1 upon n. The Newton constant is given by 1 upon n squared. And the target space entanglement involves n squared degrees of freedom. So it's natural to expect that the answer in fact scales as n squared. So this motivated us to guess that the leading answer in fact saturates the Bekenstein bound. So namely, you take an arbitrary region in the bulk, and if there is a target space entanglement which is associated with this region, the answer would be given by the area divided by 4 times the Newton constant. This kind of conjecture has been made earlier, most by Jacobson and by Bianchi and Myers, with trying to ask the question whether generic areas which are not extremal areas are also associated with interesting entanglement. One of the issues with those discussions is that it was not clear what is being calculated, what really the conjecture is. I think one sort of epsilon progress we made is that we have been able to provide a very concrete definition of one side of this. So it is something which can be in principle disproved. As I said, we did some calculations in DP brane geometry, and the conjecture does lead to results which are reasonable. So let me finish by saying that an understanding of target space entanglement and its relation to approximate notions of bulk entanglement, I think, lies at the heart of understanding bulk locality. We have discussed some notions of such entanglement and speculated about its possible connection to a notion of a bulk entanglement. We have path integral expressions which can be used to explicitly calculate this quantity numerically. Apart from this connection to gauge gravity duality, I think our notion of target space entanglement is possibly a useful concept in many body theory and in quantum field theories in general. That's all I got to say. Thank you very much.
Can I ask a question?
Sure.
Yes. So maybe related to this bulk locality. So by using your method, is it possible to obtain some diesel brane distribution in the bulk? I think even such simple question is non-trivial because usually we cannot diagonal all the components. So how do you think this simple?
You know, as
simpler
far as
question?
I can see for real D0 branes for the BFSS theory, the only reliable calculations are probably numerical. I mean, this is why we spent a lot of effort, trying to have very concrete formula for, for this entanglement, for the Renyi entropies. So I think, but I don't know, you know much better than I do. I mean, you and many other people have some approximate wave functions, for the D0 brane system. I don't know whether they will actually give some reliable result, but it might give some indications. It's quite possible, I think. I mean, one of the things I think we looked at briefly is, I think, actually your work with Gautam on the large D, which at least there is some framework in which there's some limit in which that approximation is exact. Of course, your things are all running in terms of correlation functions and path integrals. It's not very easy to translate it to, to the case of entanglement, I think. But I think that's one direction which can be pursued.
Have you tried any simpler model like harmonic oscillator?
Simpler models?
I mean, so for example, in bosonic model and x dot square plus mass times x square.
Right.
This kind of very simple model.
One of the things which I want to do, which I haven't done, is actually the BMN version of the bosonic model, which is very similar, where you have actually an x square potential, which makes the model much more well defined. And that model also has a phase transition, which might reflect properties of entanglement entropy. I think that's a very interesting direction, which I would certainly like to consider. Yeah. I think in that case, that model with the x square in it, I think would be interesting because
for just a toy model.
Thank you. I think there is a question from Shaheen. Shaheen,
Yes.
So very quickly, please, because we need to go to the next talk.
Sure. So I have two questions. One is whether your analysis can shed any light on the question of transverse fibranes in the BFSS matrix theory. And this second question is whether your analysis is going to shed more light on the black holes. As you know, BFSS has black holes, and whether it could be relevant to the information problem. So these are the two questions.
As for the first question, I don't know much about the construction of transverse fibranes. one thing we are looking at briefly are fuzzy spheres, like of the Myers kind of form, on which you yourself are an expert in. So, and try to see whether, I think these notions are actually useful in trying to, could be useful in trying to understand entanglement in non-commutative field theories in general, because, it's written entirely in terms of the matrix constructions. But, I really don't know much about the construction of the transverse fibrate to say anything about that. And about the second question, yes, of course, I think that's our hope, that it will tell us something about the black hole problem, because if it really provides a more well-defined notion of entanglement across the horizon, I think that certainly would be very useful. But I think we are pretty far from that. I mean, it's not. It's something we hope we will do. We will be able to show that it has some meaning.
Okay, thank you very much, Sumit, for your nice talk and answering the questions. On behalf of Dawood Moumni, I would like to thank you for your participation in this slot. He had to leave and left the chairing of this session to me.